Hello and welcome back to California Geology. I am Dr. Robert Lopez. Today I want to talk about the Death Valley region and the highly extended terrains that occur there. So here's the turtleback surface right here. This is actually the Badwater turtleback. So here I'm actually at a weather station in the middle of the Death Valley Playa. See all the salt flats here. And so Badwater Road is back over here, and here's some alluvial fans coming off the Black Mountains here. And so these are rock formations along the east side of Death Valley, near Badwater, in the Black Mountains. Precambrian rock, about 1.7 billion years old. There's also some other rock that's about 1.4 billion years, some igneous plutonic granitic rocks that intrude these rocks as well. These are some of the oldest rocks found in California, and so they're going to tell us a story later on here. Again, they're shell-shaped, possibly caused by compressional and extensional forces shearing in the Death Valley and Furnace Creek fault zone. So another thing that's going on here, there's a fault zone at the base of these mountains that has some strike-slip component to it. And so that could be causing some compression. In fact, I'll show you that fault scarp here in a minute. And then the Paleozoic and Neoproterozoic cover is missing 20 to 30,000 feet. Again, based on those geobarometers of those late Cenozoic intrusive. It's a diorite. In fact, part of it's right in here that intrudes into the older core of these turtlebacks. Now, if we look at a map here, this is a general map, geologic map of the Death Valley region. Here's Death Valley here. And so the different colors refer to different rock formations. And so what I want you to focus on are these late Paleozoic Pahrump group, Paleozoic and late Paleozoic sedimentary rocks. And you can see that those are going to be exposed in the Black Mountains. Also, this is Precambrian metamorphic rocks. So here are the Black Mountains, right, in the turtlebacks. So here are the turtlebacks right in here, and we'll see these Precambrian rocks. Now, note that the blue rocks, the Paleozoic and late Proterozoic sedimentary rocks that are missing, they're nowhere to be found here, at least in this part of the Black Mountains. Right? So Furnace Creek would be back over here. So where are those rocks? You can see that there's some a little bit down here to the south, so that's evidence that they used to be here, but they should be in large amounts, great thicknesses, 20, 30,000 feet. But then when you look over here to the Panamint Range, which is to the west, so here's Death Valley, here's the Panamint Range, P for Panamint Range, there's a whole bunch of them here, right? So geologists speculate that they were once here and have since been moved to this position here. So this map is just showing that the Paleozoic rocks and Neoproterozoic rocks are missing from the Black Mountains. Again, here are our turtlebacks. Badwater, this would be the Cotton Canyon, and then the Mormon Point here. Now, this is actually from your textbook. And what I want you to look at this picture here, note that there's these little blocks, right? So here's a little block here. So it's like, so this surface used to be parallel with this surface, which used to be parallel with this surface. So these lines here. So these are like books that were standing straight up and have since leaned to the left here. And so this is the Detachment fault coming right through here. So these blocks are sliding down, sliding down. This is in the Death Valley region. And so what you're seeing is this like here. The surfaces sliding down, right? So like this surface could be something like this guy down here, and then this surface up here could be like this one up here, right? So we're seeing that that detachment surface. And another cartoon down here is showing how there's this myelinite forming in the lower plate, right? Where you're seeing this ductile deformation, right? And you're starting to see, remember incipient means it's starting to form, this myelinite, and then that's brought to the surface by this detachment faulting. Again, we're looking at about 10 kilometers depth here, where there's high enough temperatures. Ductile deformation, myelinite formation. Now, this is a picture of Badwater that I took a few years ago, and here's the Badwater fan here, and here's the Badwater Road, and you can see the scarp. So here's the scarp. So the Death Valley fault zone goes right through here. And this is, again, evidence for recent faulting. So again, a geologist would see this scarp and say, this is an active fault because there's a prominent scarp exposed here. Here's another picture of that scarp. Here's the bad water again, and here the prominent fault again. Now, this is an aerial photo looking at the Copper Canyon turtleback here, and we're looking toward the north, and you can see here the Cenozoic or tertiary rocks that are covering this Precambrian basement. So all these rocks were much higher and have slid off, slumped off with that detachment faulting. Then here's another one. This is the Mormon Point turtleback right here. So again, this is a contact between these younger Cenozoic rocks, which are only a few million years old, and then you got these rocks down here that are 1.7 billion years old. So quite a drastic change there. And then this is an aerial photo of that Death Valley fault zone. You can see it's a very linear fault. So when geologists see something like this, they know this is evidence of recent faulting. In fact, you can see part of a scarp on this alluvial fan right here. So very recent faulting, very young mountain range, actively being pushed up. Beautiful alluvial fans in here. Now, a picture I've kind of edited, a picture I showed you earlier from the deserts where we're seeing these detachment faults, right? Here's the big detachment fault. And here are the listric faults that are joining it. Remember listric faults? And so this detachment surface is moving up, exposing those mylonites in here, and then all those rocks that were once higher up here have been slumped off, right? Now, here's another model showing that same process where you're having this detachment fault, and then there might be some isostatic uplift because the temperature changes. Remember, because you unload, for example, if you're on a little boat and on the water and you step off the boat will isostatically uplift. So as you remove weight, there's going to be some isostatic uplift and there's going to be some crustal rebound, and you can expose these deeper seated rocks. So that's how we can get these mylonites also to be exposed at the surface. We kind of strip away through these detachment faults this younger cover, and we expose the Precambrian basement here. Again, the turtlebacks right here. So again, we're stripping away, exposing that Precambrian basement. Well, let's stop here.